Okay. So we finished last class by seeing the definition of a polytope. And now what I want to do is explain to you why that definition makes sense and why it matches the ideas that you might have about polytopes. So here's what I wrote. So I said a polytope is something of the form P equals convex hull of some points which I'm going to call V1 up to Vn. And I wrote this formula for it, right? So I said that this was going to be the set of points in R to the D such that there exists lambda 1 up to lambda n. So let me just write lambda in R to the n such that x equals lambda 1 v1 plus dot 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 plus lambda n bn, right? Where the lambdas should add up to 1, and they should all be greater than or equal to 0. Okay? So that's what I wrote. And what I need to justify to you now is why this matches our intuition of what a polytope is. In other words, maybe we're in our D, and I'll just draw a two-dimensional picture because that's the easiest. So you have some collection of points, V1, V2, up to Vn. Okay? And somehow I need to justify to you that this set that I wrote here is really what we think of as the convex hull of these guys, which is this polygon right here. Okay? So this is P. So that's what I want to begin by doing. Okay? Now, let me just say a little bit about notation here. So I can also write this as x in Rd such that there exists lambda in R to the n such that, and I can write this as a matrix equation. I can write it as x equals the matrix V times the matrix lambda. Okay? Where basically the matrix V that I'm thinking of V as this matrix whose columns are my vectors V1 up to Vn. Okay? And lambda I'm thinking of as a column vector like this. Lambda 1 up to lambda n. Okay? And so when I multiply a D by n matrix times an n by 1 matrix, I'm going to get a D by 1 matrix, which is going to be my point x in Rd. Okay? And I'm going to also write this as something like this. Okay? Where this one is going to be a row vector of ones. Okay? And lambda is my column vector. And so when When I do this times this, I get lambda 1 plus lambda 2 up to lambda n. Okay? And then this I can write like lambda greater than or equal to 0, where I'm thinking of this 0 with a little line on it as a column vector. Okay? So you see, I'm writing the same thing. I'm just changing the notation a little bit. And the reason for this is that I want my expressions to be as clean as possible, and I want to avoid subscripts. And so I'm going to try to stick to this kind of matrix notation as much as possible. But you should always remember that when I write a matrix equation, we're really thinking of the same thing that I wrote here a little bit more explicitly. Okay? Any questions about this notation? Yeah? That's a very good point. Just like in here, my points v1 up to vn are in R2. These guys are vectors in Rd. That's correct. Which is why I said that this was a D by n matrix. D by n, and this is n by 1. Okay, so what does this have to do with this picture? Let me show you an old calculation that you did at some point in your lives. And we're going to do it again. Okay. Let's say that you have 2 points P and Q, and this is maybe we're living in some vector space R to the D. Okay. And let's take a point somewhere in the line segment between P and Q, and I'm going to call it V. Okay? Now, like I said, because P and Q are vectors in R to the D, you can think of them as column vectors P1 up to PD and Q1 up to QD. But you'll see in the course of what I'm going to say that we're actually able to avoid all those subscripts and just stick with P and Q. We won't need any of these guys, but maybe for now it'll help you to think that they're column vectors. Okay? And let's say if you know what the coordinates of P are and what the coordinates of Q are, and now you want to know what the coordinates of V are, then what you can do is the following thing. You can say, okay, let's consider the length of the segment, and let's say that this has length lambda. Relative to the segment, this has length lambda, and this has length mu. Okay? So I'm defining lambda to be the length of VQ over the length of the whole segment, and mu is the length of PV over the length of the whole segment. Okay, and so of course, if I add up lambda plus mu, then I get PV plus VQ, which is PQ, over PQ, so 1. So here I might be saying, this is 1/3 of the way, this is 2/3 of the way. And those numbers I'm calling lambda and mu. Okay? And now I would like to compute the coordinates of V. Do you guys remember? So I think probably at some point in your life you had to memorize this formula. Does anybody remember it? I didn't. I had to work it out. Does anybody? It's almost. It's the other way around. So that's what I thought it was, and then it's the other way around. So let's just work it out, and let's see what we get. The way you do it is you say, okay, well, look at the vector V minus P. Okay? So that's a vector like this. Okay? And look at the vector Q minus P. Okay? So that's this whole vector from P to Q. Okay? So of course the vector PV is just mu times the vector PQ, because they have the same direction, but it's only mu of the length. So V minus P equals mu times q minus p. Okay? And so then I say this gives me v equals p plus mu q minus mu p. So I get 1 minus mu p plus mu q. So that is lambda p plus mu q. Okay? So those are the coordinates of the point V, and you see that I can write them without any reference to the actual coordinates, just in vector notation. Okay? So this is V. But then the two things that I'd like to point out to you is that first, lambda plus mu is equal to 1, like I said there. And also, lambda is greater than or equal to 0, and mu is greater than or equal to 0, right? Because they're ratios of lengths. So if you look at this expression, okay, you see that if you want to express any point in the line segment between P and Q, any of these points, you're going to represent them as a combination of P and Q, a linear combination, lambda P plus mu Q. But it's not just any linear combination, it's what we called a convex combination. A convex combination is when the coordinates, when the coefficients add up to 1, and they're greater than or equal to 0. Yeah? So this expression that we have here is exactly the same kind of expression that we have here. Okay? And if you think about what I did there, what I did there is exactly the one-dimensional version of this. And so really, I am proving that this set that I'm describing here is really what we think of as the line segment. So line segment agrees with that funny set that we described over here. Right. Any questions about that? Maybe a small exercise that I'm not going to collect, but that you might find instructive, is that this also works, well, maybe let's not crowd the board here. This also works, for example, if you take 3 points, P, Q, and R. Okay? And I want to define the polygon that they defined, this triangle. Okay? And so what happens if I consider some point inside this triangle? So let's again call it V. Okay? Well, what I'm telling you is going to happen, and I mean, this is a kind of an offline exercise, is the following thing. If you look at the way that the point V splits up my triangle into 3 little triangles, and let's write what fraction of the area is inside each of these triangles. Okay? So for example, I'm going to say that lambda is this area, is the fraction of the area in there. So lambda is the area of VQR over the area of my triangle, my big triangle. Okay? So this piece is lambda, and then similarly, this fraction of the area is mu, and this fraction of the area is nu. Okay, so I define mu similarly, and nu similarly. Then, through a little bit of calculation, you can prove that the coordinates of the point V, in terms of P, Q, and R, can be expressed as lambda P plus mu Q plus nu R, where lambda, mu, and nu are the numbers that I just defined. Okay? I'm not saying this is obvious. You have to compute, but this is what you would get. Okay. And then again, because we're talking about the percentages of the area, if you add up lambda plus mu plus nu, you're going to get the full area. So that's 1. And because these are areas, these numbers are greater than or equal to 0. Okay. And so again, in 2 dimensions, what I'm writing here shows that the mental picture that we have of a triangle, of a convex hull, matches with the equation that I have over there. Okay? And basically, you can turn this into a proof that the intuition is really matching that definition. And so this is why we call this a polytope. Any questions about that? Yep.
Why don't we use a strict inequality for the lambda vector greater than 0?
That's a good point. Why do we allow lambda to be equal to 0?
Lambda sub I could be equal to 0, but the lambda vector you're saying is greater than or equal to 0. Why should that just be a strict inequality?
By the way, so maybe before I answer your question, I wrote this without saying exactly what it means. What does it mean for a vector to be greater than or equal to a vector of the same size? We mean that each entry is greater than or equal to the corresponding one. Okay. Oh, I see. So maybe I did answer your question then. But let me make the point that some of these lambdas could be 0, because, for example, if lambda was 0 in this example, then V would be the point Q, which belongs in the convex hull.
The second question is that's called barycentric coordinates, right?
Absolutely. So if you've heard of this, then these are called the barycentric coordinates. And you might know that barycentric coordinates are not only true, they don't only exist in the plane, they exist in any dimension. And that's almost equivalent to saying that my definition of polytope matches with what it should be. Okay, so now we have a definition of what a polytope is. And we have this, which is good. And now I want to say something else, which is the following. Well, maybe the next thing that I would like to say is the following: that remember that when I say polytope, I mean convex polytope. Everything is convex in this class. Okay? And so later on in the class, we are not going to worry about this, but because this is the first time you see this definition, you should question this and say, okay, why is this convex? Right? Because we do have a meaning of convex. And so we need to justify that this set that I defined here is convex. And so maybe that's the next thing that I will do, is just justify to you that this thing is convex. Okay. Now, before I do that, maybe I shouldn't have erased this whole thing here, but remember what we said last time, which is that P being convex means the following thing: that if P and Q are points in my set P, then what I said is the line segment from P to Q is in there, but now I want to say that in equations, and so I just want to say, what I just erased over there. Lambda P plus mu Q is in P whenever lambda plus mu is 1, and these guys are greater than or equal to 0. So that's what it means to be convex. Okay? And so that's what I should check. And I'm going to do this proof. It's not a hard proof, but I think it's the kind of thing it's good to see at least once. So to prove that it's convex, let's say that P and Q are in P, okay? And then let lambda and mu be such that lambda plus mu is 1, lambda greater than or equal to 0, mu greater than or equal to 0. And so what we need to show is that lambda P plus mu Q is in my polytope. Okay? Okay, so what does it mean for P to be in the polytope? It means that there is an expression like this. Okay? So we're going to write P as lambda 1 B1 dot 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 up to lambda n Bn, where the sum of the lambdas is 1, and all the lambdas are greater than or equal to 0. That's what it means for P to be in there. And let me write a similar expression for Q, because Q is also in my polytope. I can write it as a convex combination of the VI's. Okay? And then what I want to show is that lambda P plus mu Q is in my polytope. And so what I have to do is just compute. What is lambda P plus mu Q? Okay? And the way that I'm going to do it is this. Well, I multiply the top one by lambda, right? And so I'm going to distribute lambda to all of these guys. And multiply the bottom one by mu. So I'm going to distribute mu on all these guys. And so what I'm going to get is lambda 1. Well, maybe I'll first write lambda P is this. And then mu Q is mu 1 V1 up to mu n Vn, right? Which I can just distribute as lambda 1 plus mu 1 V1 up to lambda n plus mu n Vn. Okay? So I just do this stuff, and I find that my point lambda P plus mu Q is a linear combination of the VI's. But I don't need it to be any linear combination. I need it to be a convex combination, right? And so that means two things. One, well, the easy thing first is that the coefficients should be non-negative, right? But you see that just by definition, because all my lambdas and all my mu's are non-negative, then all of these coefficients are non-negative, right? So that's not a problem. The other thing I have to check is that when I add the coefficients, I get 1. And that doesn't look so obvious. Okay. But let's just do it in this corner over here. What happens when I add up lambda 1 plus mu 1 plus lambda 2 plus mu 2, so on, up to lambda n plus mu n. When I add these things, I get lambda times lambda 1 plus lambda 2 up to lambda n, that's 1. Right? And when I add the second column, I get mu times mu 1 plus mu 2 up to mu n, that's also 1. Here I'm using that the sum of the lambdas is 1, the sum of the mu's is 1. And so I get lambda plus mu, which fortunately is equal to 1. Okay. Not fortunate, of course. This is not luck, right? We knew this was going to work, so it works. Okay. So sum of the lambda i's plus mu i's is 1, and that's it. So that means that our polytope actually is convex, like we said that it is. Okay. So that justifies the name convex polytope. Okay, these things really are convex. Any questions about these computations? Is that making sense so far? Okay. Let me make a comment about convex sets in general. Okay, this is the definition of a convex set. If you take any 2 points in the set, and if you take any convex combination of them, then you should be in the set. Okay? So I claim that if you satisfy this property for 2 points P and Q, then you also satisfy this property for any collection of points in your set, any finite collection. Okay? So if you have P1 up to Pn in your polytope, then any convex combination of them is in your polytope. So whenever you can choose any lambdas as long as they add up to 1 and they're all greater than or equal to 0. I'm claiming this and I'm not proving it. Again, this is a nice exercise. It's actually a useful exercise for you to practice with these convex combinations, but it's another offline exercise. I'm not going to grade this. But this is not too hard because you see, here I'm making a general statement about n points, and here I'm making the statement for 2 points. So this kind of smells like induction, right? I'm telling you here's the case n equals 2, and you can use an inductive argument to show that if this property is true for 2 points, then you can inductively prove it for any number of points. Okay? So this is a nice exercise by induction. Okay? And so maybe I will write in summary, P convex means it is closed under taking convex combinations. If you take any finite subset, and if you take any convex combination of that finite subset, then you're going to stay in the set. Okay. So why is it that I'm saying this? For the following reason. I mean, first, it's useful to know. But here's a nice statement that we can make, which I think is going to match the picture of the rubber band a little bit better. Okay? What I'm going to say is that, given points v1 up to vn, the set that I defined here, P, is the smallest convex set that contains these points. So we can think that the convex sets that contain these points have to go around, okay? And if you want the smallest one, then you just let the rubber band snap into place, and that's what you want. Okay? And so let's make a theorem out of this so that this is true. P is the smallest convex set containing v1 up to vn. Okay. Now, let me ask you guys something. What does this even mean? What does smallest mean?
Well, I'm seeing what's in Euclidean space. Measure it, right?
We're in Euclidean space, so am I talking about measuring them through some kind of volume? But you thought you signed up for a combinatorics class, and all of a sudden we're talking about measures. It turns out actually that we don't need to develop any measure, because this is true in a very strong sense. And this is the sense, so it's a set theoretic sense. So I'm saying two things. One, P is convex and contains them. And I'm also saying that any other convex set that contains those endpoints actually has to contain all of P inside it. And so it's smallest in any reasonable measure sense that you can think of. Okay? Any Q which is convex and contains v1 up to vn must contain all of P, and therefore must be bigger than P in whatever sense you can think of. Okay? Well, if you think about this, actually, we have nothing to prove. This is done, because is it true that P contains, is this first statement true? We just proved that P is convex, and obviously it contains v1 up to vn. How obvious is that, actually? So if we want it to be obvious, we have to find them inside this ugly set. So can you find V1 in this set? If you want to find V1, you have to show that there exists a lambda such that blah, blah, blah. It's not too hard because V1 is just V1 plus 0 V2 plus 0 V3 up to 0 Vn. Okay? So the coefficients are 1, 0, 0, 0. They add up to 1, and they're not negative. So it's almost obvious, let's say. It's not entirely obvious, but it's easy. Okay? So P is convex, and it contains V1 up to Vn. Cool. And if Q is convex, and Q contains V1 up to Vn, then by this property, Q has to contain any convex combination of V1 up to Vn. And P is exactly the set of convex combinations. If you look at what I wrote here, this is exactly P. Okay? And so this, what I'm saying here, too, is synonymous to doing this induction, basically. Okay? And so this shows you that that this rubber band idea is also accurate. Okay? This is the smallest convex set containing your points. Okay? So that gives us two ways of thinking about polytopes. Okay. Any questions about these definitions? Okay. One thing that you'll see about this subject is that it's kind of bipolar, in the sense that, for example, if you look at your book, depending on where you open the page, you might think you're going to really like this class or you're really going to hate this class, according to what your preferences are. Sometimes you open and it's just a sea of equations, and sometimes you open and there's just these beautiful pictures. I guess that shows my bias. And it kind of has to go back and forth. And so what I just wrote here, you might think of it as a sea of equations, but we need to know that it matches the geometric pictures that we're going to draw. Okay? But I think maybe a good goal for the class would be that in every class I do some algebra and I do some geometry. And so let's actually draw some pictures now. Okay? Now that we know what a polytope is. Okay? So I'm just going to erase all of this. There's a really funny line in the book. I think at this point in the book he says that he's going to go and let the polytopes strut their stuff. That's exactly what we're going to do right now. I'm going to just show you a bunch of polytopes, so that we have some nice examples to work with. Okay. So examples of polytopes. And I think we should not be constraining ourselves to the plane and three-dimensional space anymore, because now we have a definition that works in any dimension. Okay? So my first example is going to be what we call the standard D Simplex. And we write this one capital delta sub D. Okay? And this family, in a sense, starts with a triangle. Okay, that's the two-dimensional member of the family. The three-dimensional member of the family is the tetrahedron. Okay. Now, what do you prefer, to move forward or to move back? Actually, what I did is supposed to work in any dimension, so we should also be able to go back. So what's a one-dimensional simplex? What do you think? In one dimensions, we are on a line, and there's not a lot of polytopes on a line. If you're on a polytope on a line, you're either a segment or a point. Okay. Turns out that the segment is the one-dimensional simplex, and the point is the zero-dimensional simplex. And if I want the four-dimensional simplex is going to get a little bit trickier to draw it. And I'm going to draw it, but I don't know. Maybe it's not a lot of information. But you see, every time what you do is that you add a point and connect it to everything that you had before. Here I added a point and I connected. Here I added a new point and I connected. Okay? And so if I want the next dimensional simplex, then all I have to do is just add a point and connect it to everything. And that's going to be a picture. So I'm going to add a point and go like this. And somehow that's meant to be a 4-dimensional simplex. What's the actual definition? Well, I just need to tell you what the vertices are, okay? And the vertices are just going to be the unit vectors. E1, E2, up to E sub D plus 1. Okay? And so these are the unit vectors in R to the D plus 1. Unit vectors. So just as a sanity check, let's see what delta 2 is supposed to be according to this. So delta 2 is supposed to be the convex hull of E1, E2, and E3 inside R3. Okay. Okay, we can draw R3. That's not too hard. So R3, maybe these are my coordinate axes, X, Y, and Z. Okay. My unit vectors are maybe here, here, and here. And then I'm taking the convex hull of those guys. And so what I get is this. And that is a triangle, so that is what we expected it to be. That's delta 2. And it's a little bit funny that actually the most natural way to define this guy is by making it live in a dimension higher. So for example, the way that I'm defining delta 3 actually is living in 4-dimensional space. Okay? But the advantage to that is that what I defined here is an equilateral triangle. We agree just by symmetry this thing has to be equilateral. And this is going to be true actually in any dimension. That's why I define it to be like this, so that it's regular. We won't talk about regular polyhedra right now, but this is the easiest, this is the nicest version of the D-dimensional simplex, which is why we call it the standard one. Okay. So let me ask you something. So I'm defining an object that is d-dimensional inside a d plus 1 dimensional space. Right? For example, here is a 2-dimensional object inside a 3-dimensional space. How can you tell that this guy is 2-dimensional? I mean, I guess one way is just to look at it, right? But that's not gonna take us very far, because already for the next case, we're going to be in 4 dimensions and we don't really know how to look there. So how could you argue algebraically that this thing is in 1 dimension lower? In other words, what you're going to do is you're going to tell me, look at this 2-dimensional plane, and all the points live in that 2-dimensional plane. Yeah?
Also, we might know that the convex hull is a subset of the affine hull.
Uh-huh. So what is affine hull?
So that's basically all of your linear combinations of your.
So we'll get to defining affine hull precisely, but affine hull is basically if you don't constrain yourself to the inside of the points, you just kind of keep going. Okay, so instead of looking at just the triangle, you just take everything on that plane. That's called the affine hull. Okay? So what you're telling me is that triangle is inside the affine hull, which is a plane. Can you tell me the equation of that plane? So this is a plane, right? This is like a linear algebra question. What's the equation of that plane? It goes to those 3 points. Exactly right. And you might remember that there's some complicated method to do this in general. I mean, it's not complicated, but it takes some work. But here you can just stare at it and say, oh, look, all those 3 points satisfy the equation, x plus y. Or maybe because I call these E1, E2, E3, maybe I should call these X1, X2, and X3. And the equation of that plane is X1 plus X2 plus X3 equals 1. Every unit vector satisfies that the sum of its coordinates is equal to 1. Okay? So I'm in a three-dimensional space, but once you specify one equation, you know from linear algebra that you cut the dimension down by 1. Okay? Now you're in one dimension lower. And that's exactly what happens here, that even though we are in d plus 1 dimensions, you can right away tell me an equation that all of these points satisfy. And it's basically the same equation. The sum of the coordinates is equal to 1. Right? All of these points satisfy, every unit vector satisfies that the sum of its coordinates is 1. And that means that even though this guy lives in d plus 1 dimensions, it doesn't have a chance to be full dimensional. We already brought it down by 1 dimension. Okay? Now, once you specify that the sum of the coordinates is 1, actually, you can see that the plane satisfying this equation is that blue plane, right? And so now, what part of the blue plane is my triangle? Basically, imagine that the blue plane extends infinitely in every direction, but then you would have to say, okay, I'm on that plane, but I'm on this side of this line, I am on this side of this line, and I am on this side of this line. And if you have satisfied those three things, then you are in the triangle. In other words, what I'm saying is my x1 coordinate is positive, my x2 coordinate is positive, my x3 coordinate is positive. That means being in the first quadrant. Octant, thank you. Okay, and that completely describes my simplex in a different way. Okay, and the same holds true here, that a different way of describing the standard simplex is by saying you have to be on this special plane where the sum of the coordinates is 1, and then you have to be on the positive orthant, is what they call it in higher dimensions. This equality is not obvious, so this giving you a lot of little exercises to fill in. But again, this is a very good exercise, and actually in the homework there is a very similar problem to this one, so it's good if you work this one out as a warm-up. Okay? But what I'm saying is that to be in the convex hull of this is the same as to satisfy this equality and these inequalities. Okay? So these are two ways of defining the standard simplex. Any questions about the standard simplex? Okay. Our second family of polytopes that is very important is the family of cubes. Okay. So I mentioned to you last time that there is a cube in any dimension. And again, the way that we start, well, the thing that we normally call the cube is three-dimensional, right? And I think if I forced you to choose a polygon and give it the name of a 2 cube, you would probably choose the square, not the heptagon, right? So that's the 2 cube. And if I force you to choose the 1 cube, again, you don't have a lot of freedom because it has to either be a line or a segment or a point. And actually, the segment is 1-dimensional and the point is 0-dimensional. So that's how the family starts. Now, I'm going to draw the 4 cube for you. And how does this go again? well, let's look at how you draw the d cubes from the direction on. Okay, so you start with a point, and then here what you do is that you draw another copy of the point and you join them together. Now to go from 1 dimension to 2 dimensions, you take 2 copies of this guy, the bottom one and the top one, and you connect them together. To go from 2 dimensions to 3 dimensions, you take 2 copies of the square, the front one and the back one, and then you connect them together. And this also is going to work in the next dimension. If you want to draw the 4-dimensional cube, then you take 2 copies of the cube, and the hardest thing is just to choose a position so that you don't make too much of a mess. 2 copies of the cube, and then you connect corresponding vertices. So this one with this one, this one with this one, this one with this one, this, like this, like this, and like this. That's it. You should do it, actually. I think this is a fun thing to draw. And actually, I think it's also a fun picture to stare at and try to understand. The problem with the 4 simplex is that you don't see anything. But I think here you can see a lot more cubes than you might have expected to see, and there's a lot of stuff you can think about. I think this is the starting point if you want to try to visualize things in 4 dimensions. This is a good example to stare at. How do I define this polytope? We call it C sub D, and we define it to be the convex hull of the set plus 1 minus 1 to the D. Okay? And this should look a little bit strange, but what am I saying here? I'm saying, so this is the Cartesian product of the set with itself D times. In other words, what you're doing is each element of this set is a D tuple, where each element is a plus 1 or a minus 1. So for example, if I'm talking about C, let's do C2 because C3 is already a little bit hard to draw like this. C2 is the convex hull of, you have 2 coordinates and they're either plus 1 or minus 1. So it's either 1, 1, 1, minus 1, minus 1, 1, or minus 1, minus 1. Okay? And if you plot these 4 points, then you see that they are exactly square. This square. The 3-dimensional picture is easy to draw, but maybe not so much on the board. Okay. Can you kind of see the? Let's just draw it. Actually, this is not so hard. The 3-dimensional guy is this cube where the origin is right at the middle, right? And so it's just like it goes through the like this, and to the front like this. Can you kind of see that? So it's the cube centered at the origin. Okay? So I'm telling you what the vertices are, but another way of describing this cube is by telling me what the walls of the polytope are, what the walls of the cube are. You know that the cube, this one has 6 walls, and can you tell me what the inequalities are for this guy? What are the? For example, if you want to say that you're below the ceiling, then what's that inequality saying? The z coordinate should be at most 1, right? And it should be at least minus 1. And the same for every coordinate, right? So another way of saying this is that this is the collection of all points in R to the D such that each coordinate is between 1 and 1, minus 1 and 1. Okay? So this clearly matches in 3 dimensions. And actually, this is a graded exercise. So this is one of the homework problems, is to show that in any dimension, these 2 descriptions actually match. Okay? And so that's what we call the d-dimensional cube. Okay. Any questions about the d cube?
Yeah, why don't we put it in solid order?
Maybe this is the answer, my number 3. That's a very good point. I could have just chosen convex halls of zeros and ones. But it turns out that it's nice to put it there for the following reason. I want to define something called the D Hyper Simplex. Okay. It's written like this. Okay. And what it is kind of like reversing vertices and inequalities. Okay. So for example, here the inequalities are at 1 and at -1 for each variable. And so here what we do is that we put a vertex at 1 and at -1. So what we get is the convex hall of E1 and minus E1, dot, 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 up to En, Ed, and minus Ed. Okay. And you might be familiar with this construction in 3 dimensions. What am I doing? I'm considering a vertex at each unit vector and its negative. And if you look at that in that picture, what I'm doing is that I'm putting a vertex at the middle of each face. Okay. So I'm putting a vertex right at the middle of each face. Okay. And if I draw this properly, then what you should see is an octahedron. It's not too bad, huh? Can you see it? That's the octahedron. And the reason that we like to put the cube here is so that this works out to be a nice place to put the octahedron. So this is called the Hyper Simplex, and in general what we do is this in any dimension. Okay? So these are the vertices, but I can also tell you what the inequalities are. Okay? And the inequalities are given by all the points in Rd, such that the dot product of x with any of those vectors should be less than or equal to 1.